Now, historically, students in university found related rate problems really, really difficult and really scary, and they didn't like them. Okay? I feel that what we have done leading up to this, how well we've learned implicit differentiation, how well we've learned the chain rule, it's not going to be that bad. In fact, you might like them. Okay, but here is the idea. Okay? You're going to be given the rate of change of one thing and asked to be found the rate of change of another quantity. For example, if I took a balloon full of air, but it had not tied it shut. You remember when you take that balloon and then you pull it and it goes, like it squeals, right? That's very fun. Everybody has had that experience where they let the air out of the balloon squealing. Well, we could let the air out at a constant rate. If you stretched it just perfectly, it would let the air out at a constant rate. What happens to the balloon as you let the air out? It gets smaller. So as the volume is getting taken out, the balloon is getting smaller, which means that its radius is changing, its circumference is changing. So I might tell you the volume is changing at this rate. How fast is the radius changing at this moment? Those are called related rate questions because you have multiple things changing and you could figure out how fast one thing is moving, well, another thing is moving, or how fast the radius is changing as the volume is changing. That makes it a related rate problem because you have two rates and they're related to each other because as one changes, the other one changes. Okay? So we'll look at a bunch of questions, but to do this, we have to create an equation that relates the two ideas, use implicit differentiation and the chain rule, and we'll be able to solve this. So here's our first question. Okay? How fast is the area of a circle increasing at the moment the radius is 100 meters and it is increasing at 2 meters per minute? Okay? So, we could look at dropping a big rock into a pool and it hits and then a ripple of a circle will go out from that. And that circle will be getting bigger and bigger and you're wondering about the area. Okay? I can think of negative practical purposes of this. Like a negative practical purpose is like dropping a bomb that explodes and causes destruction as a circle goes out. How much destruction is happening when it's at 100 meters? How catastrophic would this be? Okay? So what do we know? Well, the idea here is both the area and the radius, they're functions of time. We don't even know what their equations are with functions of time, but we know that they are functions of time. The area is increasing as time increases. The radius increases as time increases. We want to find dA dt. We want to find the rate of change of area. We know dr dt. We know that the radius is changing at 2 meters per minute. And we want to find it at the exact time when the radius is 100. So the question is, can you create an equation that relates area to its radius? Absolutely. That's your area of a circle formula. So I have an equation that relates my area to the radius, and I want to find out what dA dt is. And this is where our implicit differentiation comes into play. We can take, even though we don't know what A of t is, we don't know what R of t is, we don't know those equations, we can differentiate with respect to t on both sides. This is your implicit differentiation. How do we do implicit differentiation? Well, if a was a function of time, what's the derivative of a? Would just be 1, and then you would get dA dt. What's the derivative of r squared? Well, you would put the 2 out in front, subtract 1 from the exponent, then what's the derivative of r? dr dt. This is basic implicit differentiation. Except instead of using variables of like y and x, we've got t's and a's and r's as our equation. We wanted to find dA dt. We wanted to find dA dt. Do we know dr dt? Yes, we know that's 2. We want to find it exactly when the radius was 100. So we can plug things in. I left my answers exact, 400 pi meters per meter squared per minute, or I could change it to a decimal and get 1,257 meters squared per minute. So if we think of this catastrophically with the bomb example, what are you actually destroying? 1,257 meters squared. You can imagine how big a meter is, how big that square is, per minute. You would expect in the next minute that much more area to be destroyed. Okay? This actually I don't think is moving very fast. Have you ever seen, like if this was an actual bomb thing, it's a very slow bomb that the explosion traveled this distance in a minute. You could probably outrun that bomb. That would be a safe bomb. Like, we're dropping a bomb, we're going to destroy all the infrastructure, but you will have enough time to run away. But I don't think they make any of those kind of bombs. Right? What would probably be a better unit here? Seconds? Yeah, then you probably couldn't outrun it. Okay? But these kind of calculations, like, I guess they would do, people who, like in wartime stuff, they would be like, if we do this, what's going to happen? This is the math that they would be looking at, rates of change. What could we expect the destruction to be in a certain amount of time? Okay, second example. Let's go back to balloons and birthday parties. That sounds a little bit more pleasant and nicer. A balloon is 30 centimeters, and you've got the perfect spherical balloon, because we don't want to get into hard math yet. I don't know what the official formula for one of those balloons that has like that little extra bump and this kind of, they probably have a formula for it somewhere. We could probably create it in a couple units, don't worry. Calculus is pretty powerful. But right now we'll keep it nice and spherical and easy. And you're inflating it so that its radius is increasing at 3 centimeters per second. How fast is the surface area of the balloon increasing? So we have two things here. We have area, our surface area has to be a function of time, and radius has to be a function of time. They're both changing with time. We want to find dA dt. We know that the radius is changing at 3 centimeters per second. What's going to be the hard part for you in this unit? Formulas. Do you remember your volume formula and surface area formulas of a sphere? You know volume? Okay. So what was the volume? 4/3 pi r cubed. Nice. Oh, I'm going to show you something today that's going to make you smile, I hope. Like that's so cool moment. Does anybody know the surface area of a sphere? Surface area is 4 pi r squared. What is super cool about the volume of a sphere and the surface area of the sphere now that you are enlightened calculus students?
Is the derivative?
Surface area, which is one dimension down, is just the derivative of the volume. That's crazy. In a circle, what's the area of a circle? One dimension down would be? Oh my goodness. The circumference? And it's just the derivative? Ah. Which is kind of cool because if you remember your volume formula, you also now have your surface area formula of your sphere. Very cool. Very, very cool. So, rate of change questions. We list out our quantities. We want to find dA dt. We know dr dt, and we want to find it specifically when r is 15. How did I get 15? Half of the diameter, right? When the diameter is 30, the radius would be 15. Can we create an equation that relates the two? Absolutely. It's 4 pi r squared. Implicit differentiation with respect to time. Derivative of A would be dA dt. The derivative of A is 1, but then it's a chain rule, because you'd have implicit differentiation, you have dA dt. So every variable is going to, implicit differentiation, you're always going to end with a dA dt. When the r is the variable, you're going to end with a dr dt. The 2 comes out in front, subtract 1 from the exponent, and then you have a dr dt. And then it's just a matter of plugging in your 15, plugging in 3 for dr dt, Have you ever challenged yourself to keep blowing up a balloon until it actually pops? It's like nerve-wracking and exciting at the same time. As it's getting bigger, you know that any moment it's going to explode. But try not to react with like totally scared completely. Try not to be scared when it pops. Try to be like calm and just blow that up and let it, no reaction whatsoever. I think it's impossible. I think your body automatically goes through this chaotic convulsion when it explodes. Sounds like something you should try on your own. Definitely. What did you learn in math today? How much fun it is to have a balloon explode in my face. Awesome. Okay. We're going to do 2 more, and then I'm going to give you some time to work on your pretest and look over your checklist for tomorrow. For tomorrow's test, if you would like to start early in break, you can come early right at the beginning of break. If you don't have a period 2 class and you want to sneak in early during period 2, feel free to do that. You can also work into lunch if needed. Okay. Gravel is falling on a conical pile, which is the natural shape that would happen if you started pouring sand or anything off a conveyor belt. It'll make a nice cone. But as you pour more stuff on there, what happens to the cone? It gets bigger. The height will get taller, but so will the radius at the bottom. And so will the volume. So we have 3 related rates here. Height is changing, radius is changing, volume is changing. Gravel is falling on a conical pile at a rate of 4 meters cubed per hour, so that the diameter is always double the height. Find the rate of change of the height of the pile at the moment the height is 3 meters. So what we're trying to figure out here is, if you were doing this, once the height hit 3 meters, how fast is it actually changing at that moment? What could you expect in the next hour? So what do we have? We have volume is a function of time, height is a function of time. Technically, diameter is a function of time, radius is a function of time. We have a lot of different variables that are related here. We're going to want to try to create an equation that just has volume and height, because we know that the dv dt is 4, and we want to find the dh dt. What were we given? We know that the diameter is always 2 times the height, because the diameter is always double the height. We also know the diameter is always 2 times the radius. So this would mean that the height and the radius are always the same. So if we want to find it when the height is 3, we would also know the radius is 3. We would also know the diameter is 6. Does anybody know the volume of a cone formula? No? Does anybody know that? I find the volume of a cylinder formula easy to remember. Do you know the volume of a cylinder? You want to see that side? Volume of a cylinder is the bottom, which is pi r squared. And if you kept stacking up papers that were circles, times that by the height, that would fill up that whole canister. And volume is something that fills up something. So taking a bunch of pieces of paper and filling it up makes a volume. And that's what the idea is. Pi r squared is that circle, times by that height, creates your volume. The cone is like taking this out of there. And it takes out the volume of the cone is, well, I have it right here, 1/3 the cylinder. There's so many YouTube videos of people taking cones filled with water and pouring into cylinder 1, 2, and when they get to the 3rd one, it fills up perfectly, and everybody's like, super excited. Now, originally, our formula has an R and an H. But since we know that the H and the R are the same time, it makes sense for us to substitute. So we just get a formula with just volume and just height. And now we can do our implicit differentiation. Take dh of both sides. We want to find dh dt. We know the H, we know dV dt. It's just a matter of plugging things in and solving. All right, we'll do one more and then I'll give you time to work. Oh, will this ever happen again for us over the next couple of months? Will it ever warm up enough that a snowball could melt outside? No, but we could make one and bring it inside. So you make the perfect spherical snowball. And then you bring it inside and set it up on an apparatus so that it's spinning perfectly so it melts symmetrically. This could take some skill. Because if you just let it, it'll like drip one, you know, it just sort of like keeps spinning it. So theoretically, I guess this could be possible. Its volume is decreasing at 1 centimeter per minute, centimeter cubed per minute. At what rate is the radius decreasing? At the moment the radius is 5 centimeters. So I'm just imagining a 10 centimeter diameter. This is a pretty significant snowball that we started with. Like it might be even, it might be like snowman head size to start with. So what do we have as our quantities? Volume with respect to time and rate with respect to time. Both of those are changing with respect to time. What do we want to find? We want to find dr dt. What do we know? We know dv dt. We want to find it specifically when the r is equal to 5. Do we have a formula that relates volume and radius? Well, we talked about it earlier. Do you remember it still? 4/3 pi r cubed. So we could do implicit differentiation. You want to try that next step on your own, see if you get the derivative? If you're not done, don't look, but if you are done, check. Did you get it right? And then you just plug in everything that you know and can solve. It is not melting super fast. The radius is not changing super fast at this moment.